going. Oh, that looks cool.
Michael Furyik from DogFab is with us. He's the guy that made most of those cool oversized gas lens cups that I've been using and I've showed you guys before. He's also got some other tools we're going to show you today and tricks for making this stuff go together way better than I've ever done it before.
Hey, we're going to shed some light on some techniques that we use to build professional race headers. We're going to show you guys some of the professional tools we use, and we're going to have fun. I'm going to kind of let these guys take over and do most of the work, and I'll just supervise and just kind of show and give a direction and how is the proper way to do it.
Yeah, if you hadn't guessed by now, he's really good at this. We're about to level up our header building game right now. Tip number one. It's pretty much step number one. You need to know where your beginning and your end is. Here's our flange. We got this from stainlesssteelheaders.com. This is laser cut to the port design of our LT4, which, dun dun dun, not round. So that's not going to exactly want to go together there.
The tubing that we're going to use is 2 1/8 inch tubing. It's 304 stainless 16 gauge 065 wall. The flanges stock are set up for a 2-inch OD where the tube would actually fit into the flange. Even though it's oval, the circumference of the hole or the runout would allow us to bend and beat around a 2-inch and fit it all the way through. The 2 1/8 inch, if we wanted to, we could fit it up flat and then weld it. Basically, we could beat it around and match that port. So what I ended up doing, instead of opening up the whole hole, because I'd like the tube to recess into the stainless steel a little bit, and that will aid in better welding and a little bit more strength, I pitched it up onto the bridge port and I cut a channel and I beat around a tube so that can fit in a little bit. And that gives us a little bit of leeway that if our bend or our straight is not exactly perpendicular to the tube and we have a little bit more run out, this will allow us to have a little bit more surface and we could beat around and fit that tube into that socket real good.
And then step two, find the end of your exhaust, which in our case is going to be this stainless steel merge collector that we have temporarily mocked up with some scrap metal that's welded to the firewall of the truck. Collector's sitting there now. We know that we can turn our steering almost to the lock without contacting it. We know that's approximately where we want the exhaust to exit because, big surprise, we're going to have hater pipes on this thing, so they're just going to go right out through the fender. So that is now in place. There's the end of our exhaust. Our flange has been modified. It's in place on the cylinder head. There's the beginning of our exhaust. Now we have to figure out how do we cut all these cool bends and make them fit in a way to snake all the primary tubes around the steering, around the frame, around that dry sump oil pan, all the things that are in the way here. We're going to do that right now. This tool here is going to make it so that we'll know exactly where we're cutting these and where we need to be cutting them so that everything fits together better when we go to weld it. And the better it fits, the better our welds will be, the better our headers will be. So, can you demo this for us?
Yeah,
sir?
absolutely.
What's it called first?
Okay, it's called the Furyik Markout Pro.
Okay.
It's it has a patent pending compensator system that actually will put the bend in an engineered world on the correct part of the axes, so we could then figure out exactly where the mark is going to be. Centerline radius is finding the radius of the bend from the center to the center of the bend. And in a 180, a quick way to do that is to just take some aluminum or whatever and just do one of these deals and make 2 marks. You measure the marks and then you divide by 2, and that would be your centerline radius.
All right, so the beauty of this tool is that if you know the centerline radius of your mandrel bend, this is going to fixture it so that every time you put one of these in here, it's in the right position so you could cut it to the exact degree you're looking for. And these are the major components, right? So there's a bunch of these little plates in here. They're marked with your tubing diameter. And this wheel here you use to set the tubing diameter. And we have We go this way. We have 2 1/8 diameter tubing. Okay, so we'll set the wheel to the tubing diameter. We measured the center line from here to the center line from there. Divide by 2, that's 3 inches. So there's our center line radius, 3 inches.
On the arrow?
Oh, on the arrow.
Yes, sir.
Oh, not here. Okay. Good thing you said something. Right.
Okay.
So we lock it down, and then, in theory.
Okay. Now, the truest way to do this is to kind of view the inside of the bend. And when we look at the inside and the gap that's put on there, we try to make it so, like right now, it's hitting the inside of the bend.
Right.
So we're gonna bring it to 90, and we're gonna bring this down till it's hitting the inside of the bend. Now that thing is a true, and you see how the bend does not move as we go through the degree?
Yeah.
That's how we know this thing's exactly set right. If this thing was offset in the wrong spot, and we would run that through the degree, the tube would start to move because it'd be in the wrong arc.
Okay.
So this thing is in the correct arc. So now we would find our angle from the ledger on the board. We trace that back and pretty much line that tip up with our desired angle. And then we take a pencil and then we mark on the degree side. And then that would be, this one would be somewhere around like a 50 degree right there.
Got it.
Right?
Okay.
We mark it and we know we'd be at 50. We could fit it on the car and see if we need 5 more or 5 less.
Okay. That was my next question. Is everything I've always done is I'd take one of these and I'd cut them into like 4 pieces, and then I just go over there and turn it into a jigsaw puzzle and go, okay, this is what I need. So, is there a way to go over there and go, I need this angle, you know,
Yes.
without butchering a bunch of tubing?
You can, like, you do a big system, you'll probably have a bunch of those little random cuts where you'll find out like, okay, this is 35, this is 45, and it's just from a mistake.
Right.
They make some tools to actually help you, like the Lego set, the
ice engine,
the ice engine work.
Yeah.
It's a very powerful tool. The only thing about ice is that this actually complements that.
Right.
Where you could find out and build your header in Legos, but how do you cut it?
Yeah.
Now they offer somewhat of a bandsaw option, but nothing to this degree.
Right.
Where this thing, you could actually build a header, you could actually have a whole note on how you built it, and you don't even need anything anymore. You just need the board, you have your degree, how much straight after the bend, you cut it all, you mark it out, you cut it all, and you're fitting. You could probably cut a whole header in about 20 minutes. The one thing to remember is that no tube bend is really all that round, so it does have a little bit of tolerance in it. Like those tubes, for instance, have a little bit of ovality. That's just the nature of bending.
Yeah.
You're never going to get a perfectly round tube, no matter who's selling it to you.
Right.
When you cut it, it's going to oval even more. So it has a little bit of factor built into the actual cutout on it, and that's just, some tubes are worse than others.
This is primary tube number 2, and the fit up is actually really good, except in one area where we have a little bit of an overhang, like you can catch your fingernail on it. And if we were MIG welding, no big deal, run it over. If I didn't care, I would probably TIG weld that and just go, and it would look like all the other headers I built before today. But we now have tools and knowledge we didn't have last week, and so we're going to fix that ledge right now.
All right. Y'all could see that you have about a gauge width of steel sitting over there, and if you were to weld it, it would almost be a lap joint. But what we want to do is we want to join the levels so they are flush on top.
It'll weld better when we do that.
Absolutely.
That's the goal. Is like we're doing all these extra steps so that when the time comes to actually fuse the metal together, you have just beautiful, flat, nice welds, strong welds.
Yeah, you won't be chasing holes that could produce from having uneven surfaces. So we have this mandrel. It's pretty much a home built mandrel, same thing as y'all seen before, but it has sort of a radius that we could actually put it in the bend. So this ball here is what we're going to be finding and hitting on. We have to put this in there and then find where the seam is, and that's usually done by just feeling around and finding a step. So once I find my step, the ball's actually going to be on that side because we want to hit this down to that level. So down my step.
And again, this is just a ball bearing from a master car welded onto a piece of rock and formed to a shape that fits inside the bend. Like, you can build this tool yourself at home for, I don't know, that's probably a $20 ball bearing. They are, bud.
It's flattening out, it's flushing out. But we have to get the ball on this side because that has to go down. And we just don't want to make too many hammer marks. So having the right hammer and not putting dents on the side is critical to making a good looking system. That'll pretty much do it. Let me just clean that up with Scotch-Brite and weld it and you'll never see it. So we're going to take those little nodes out that were there and kind of okay. And once we do that, we got to make sure that this thing maintained flatness. So you see how it's got some rock?
Mm-hmm.
That just came from me just rounding that off a little bit. Actually, the material just raised up. So we're going to go back on the sander real quick and bump that and just make sure that that thing's totally flat. Okay. And again, that will help when we start tacking it. It won't pull.
So I just learned 9 or 10 new tricks on how to build headers, and because of that, #1 primary tube is about to get pronounced husband and wife, married in molten metal. That's 3 M's. It's all downhill. Alright, as you can see, tool bench is littered with tools. We're, I'd say, 1/4 of the way done with that header. Well, I'm saying 1/4 because it makes me feel good. Really, we're 10% of the way done. But here's some important things that are going on right now. We've got the first primary tube all tacked together. We're working on the second one. As I showed you before, we took one of these bends, we figured out the center line radius of it, put it in the tool, and then we made a cut. Now that we've made a cut, we've taken our piece, knocked it up in the truck and said, okay, this is really close to what we need, but we need to take about 2.5, 3 degrees off the cut we already made. And instead of just running over there and ballparking it with a pencil and going, all right, let's put this chop saw and figure out if this is right, we're actually going to accurately mark 2.5 degrees off this bend. This is the way we do it, right? I've got a line right here that we've already marked. So you would think that now this piece is so small, how are we going to put it in the machine and actually figure it out? Well, when we started, we marked the tangent right here, which is this line, 180 degrees. We marked that. So all I got to do is put it back on the tangent line, swing this to make sure it still follows the tube and it's not moving the tube around, and then I line it up with my old cut line, right, which was right here. Back where that was. So I know this is where we cut it before, which is about 92.5 degrees. Now I'm just going to swing this back, and I've already marked it, you can see it, but I swung it back and there's a little pencil line and I marked the next cut so that when I take this out, I know we're going to cut exactly that much off in relationship to the cut we already made. And that's one of the nice things about this is you can accurately make changes to pieces you've already made without, you know, a bunch of fudge and guesswork and stuff like that. So I will cut this, put it in there, and this should be pretty close to where it needs to be. Okay, now to the fun part, actually welding. Our primary tube is all tacked together. It is fitted. We believe this is the right shape and length and all that stuff that we need. And now, before we weld this, we're going to do one more final step, and that is to purge all of the oxygen from inside of this tube and replace it with argon, which is an inert gas. And we need to do that because stainless steel is a reactive metal. If we don't get the oxygen out, then all the impurities and the water grains and everything will contaminate the backside of the weld, and the weld will suck. And I don't care who you are out there. Yes, we're not building airplanes that are, can fall out of the sky, but it would be nice if our welds on the backside of the tube looked as good as the ones on the front side. It's got to be stronger, right?
Absolutely.
So Michael brought us some parts here to make this job easier, because in the past I would just wrap aluminum foil over both ends, tape it, shove a hose in there, turn on my other argon bottle and fill this, and then it tears, it rips, it leaks. It's not the ideal way to do it, and you brought some accessories here to make that job easier.
Yep.
What do we got?
Well, there's many different options you can have, and a lot of times you find yourself still using tinfoil because it's just a great product. Now, recently, Tycon, they specialize in titanium and also other accessories for welding. The purge plugs they are silicone. They actually conform somewhat to the tube and they stay in there. Now these come in silicone. You've also seen some on the market that are straight aluminum. They take a little bit more to pop in. Mm-hmm. The only disadvantage with silicone is that you cannot install next to a weld. So right. On that side, since we're going to be welding so close to the outlet, we're going to have to use the tin foil.
Right. Here
it would be fine because the weld's going to be far enough away that it won't get to about 450 degrees where it starts breaking this down.
Okay.
So quickly, we'll just install this on this side.
All right.
Okay, that's not going to pop out, and let's put our science on. Ball that thing up. What I don't want to do is have any of this touch exactly where we're going to weld, but we're going to shove that in there, and I'm also going to make sure that there's a little bit of an outlet.
Right.
So here you'll see that the gas will go in and it can escape. Yep. The trick is I do not want the gas, I don't want the pressure to build up so much in the pipe that it's blowing out the seams that we're trying to weld, because that will cause contamination and it'll just make everything junky and you won't be able to weld.
Okay.
All right, when we fill this tube up, we're going to fill it up with about 10 CFH, 10 to 15, just to get it going. We're going to let it sit for about 5 to 10 minutes. And what that's going to do is fill up the full tube, and it's going to basically filter out all the oxygen that's in there currently. And we want that tube to be 100% pure argon.
Okay, so in the past, I never waited that long. I would turn it on to like 10, wait about 2 minutes, then drop it down to 5, and then start welding, and then wonder why occasionally I get to an area where the tube would just explode. And that's probably why. That and my ill fit up. Like, my tubes have never fit together this well, so this has got to go better.
Yeah, when we start welding, we'll drop that down to about 5 to 8 CFH, just so we're not having a lot of pressure building up in the back of us. What purging does? Purging creates an oxygen-free environment in the backside of the tube. And when you're not welding stainless steel with purging, you're technically not really welding. You're just putting material on top of the tube, because as soon as stainless steel has an arc struck on it and there's oxygen behind it, it creates a crystal, and the crystal cannot form together. It actually just, the oxides will repel each other, so it becomes a brittle bottom side of the weld. So on a race car, you will have a lot of cracking if you do not purge stainless steel.
Okay. Yeah, if you've ever looked at the inside of the tube, and I think we've shown it on this channel before, where this side looks pretty good, and then you look on the back side, and it just looks like a bunch of crystals that you can actually knock off the inside of the tube, and you're not actually, like you said, you're not welding the metals together on the back side. Yeah. You're just depositing filler rod in there.
You're just putting it on top.
Okay.
So in a hot rod, regular street truck, you probably can get away with that, but with something with a lot of high heat, a lot of vibration, the tube's doing this, it's hot, it's going to eventually fail on those points.
Okay.
Your typically when you're purging butt joints, we would weld that. I'd set my welder for about the thickness of the metal, maybe a little bit less, but we'll go over that in a minute.
Okay. All right. So we're gonna back purge this. We're gonna wait a little while, and then we're gonna weld. It's gonna be awesome.
All right, this thing should be good and purged.
So less argon.
Less argon.
What do you want it at?
We're gonna turn it down to about 7.
7.
About 7 CFH. Just enough to keep it flowing while we're welding. But it's not enough to be blowing our weld.
I'm going to watch and learn.
All right, so this material averages about 60 thousandths of an inch.
Okay.
And it's spec'd at 0.65, but they do vary in thickness just because it's the gauge. So I have the machine set at about 53 amps. It's a little bit lower than the thickness of the metal. The amperage is set low because I'm gonna give the penetration time to actually do its job, where if it was set at like 150, it might get too hot and out of control.
Okay.
So I'll have way more control with the amperage every time I pulse. And what I'm gonna do is I'm gonna move my foot down for more heat every beat. And I'm gonna lift it off slightly, not fully. You'll notice if you pull it off too quick on stainless steel, it'll cause a dimple, and you don't want to see dimples. Dimples are they're cracks, basically. They're micro cracks. They go all the way through, and they will propagate. So you don't want to take it all the way back too fast. So we're gonna just ease up before I move to the next bead. I'm gonna give it some pedal, let that penetration sit. I'm gonna add a little dab of rod, let it just spread out, and then take my heat out and move and repeat. It's basically that kind of scenario.
Okay.
All right. So the machine's set. The other thing is I got a big cup. The big cups work very well on bigger diameter tube. This is a 2 1/8 again, so it should be very well suited for the size.
All right.
Every time, again, I start my weld, I'll look at that gauge and make sure we're purging. Things happen, gas bottles run out of gas. Make sure I got gas on the torch. I'll give the pedal a little blip and get the gas flowing. Okay. Comfort is key. All right, so I welded the first seam, and I figured out that the material likes a little bit of torch angle. When I first started, it wasn't as nice, so the puddle seemed to be jumping around a little bit. I adjusted, and I actually stopped being so perpendicular to the surface and laid the torch down with more angle. And what that did is it just calmed the puddle down, so it's not swirling like this. It's actually just doing this, and it became more steady and more controllable. You can see a really consistent bead pattern. So that's what I'm going to do here. I'm just going to leave the torch kind of laid over and then just roll my hand around the seam and try to go as far as I can.
Cool.
All right. It's all about torch angle. You can see the beads came in really consistent. The gas did its job, and we're getting really clean weld, really consistent beads. When I'm going over the tacks, I'm actually pausing a little bit and letting that kind of soak up the tack where we tack it, and try to get that penetration drop down. And we're going to have minor crystalling inside because we did tack without purge, but we added a little bit of rod and let that penetration soak through, and hopefully it cleaned up those tack areas a little bit. We did try not to overheat the tacks when we originally put the system together. Now, every time I pick up my helmet, I'm looking to make sure that bottle's still on and my hose is still attached, which everything looks pretty good. It's just always a game of positioning the tube to where your hand will be comfortable. and the tube won't slip out. So here we go. We don't want to do little parts of the tube and skip to other parts. We want to do it all in a consistent round, go all the same direction. We don't want to weld back in the different direction. So we just got to keep changing everything around until we can be comfortable and follow that whole tube. Again, like, I always touch down where I want to start.
Yeah.
So, like, just put your tungsten, like, pretty much where you want to start. All right, and just lay it there. And then when you're ready, flip your helmet down, and then come off a little bit, and then strike your arc.
Yeah, I'm like, for me, it's like, okay, how far can I go? That's where I seem to have trouble, is like going.
Yep. The one thing, is it hot? Is the tube hot?
No.
I would try. A good tip is that I would try to keep your hand as close to the weld that you want, because you have more control about your distance. If you're out here, you have a lot more movement for little movements, because it's basically like a triangle. So here it's really close. You got really consistent torch height and then torch angle. You just got to roll it around a little bit.
Okay. And then I feel like I need to weigh down the tube, because as I do this,
okay.
I'm making the tube.
I'm holding the tube for you. All right.
Should I start on attack?
You can, but let that amperage soak it in before you start adding rod. Like your tube's just not going to open up a hole. Okay. Let it do its job and soak in. A little bit more amps. Keep going. Keep going. Keep going. Keep going. All right. Now dip. Lay off a little bit. Come up. Dip. Lay off, move, yep, dip, lay off, move, good.
I'm going backwards.
Easy.
Look, hold on. So I'm doing the pedal backwards.
You were like looking pretty good.
I was the first. So the first, whatever you call it, tack bead.
Mm-hmm.
I pedaled it, let off, and then moved. And then everyone after that, I was pedaling it as I was moving. I was pushing it down.
Okay.
And I was like, oh no, wrong rhythm.
Yep.
White guy. I can't dance either.
No dancing.
I cannot dance. And then the other thing is, I'm gonna turn my helmet down. It was really hard. I can see the puddle perfectly. It was really hard to see the seam and what direction I should be going.
Get your head down here more, so you're looking straight at where you're going. Where if sometimes like you could be too high, but like you really need to get to the side a little bit more with your head.
Okay.
There you go.
Okay, she's welded completely, all 3 joints, and back purged with pure argon. Now we're going to show you the inside of the tube so you can see what happens when you do purge it.
So we just got done. We just turned the argon off. We let it cool for a minute, and then we turned the argon off after all the welding was done. We're comfortable that all the joints have gone around and had weld on them. The welding looked good. The tube definitely got penetrated. We should see a really clean inside with almost no color. It's about the color of the virgin metal. And when we take the purge off.
Yeah, maybe in a couple of tacks where I did it with rod.
Yep.
And no back purge, you might see some. Oh, that is good looking. That's one of yours.
I'm sure yours looks just as good. So yeah, that definitely will not break. That's ready for the fun of the road.
That is nice. Look at that. The inside of the tube, the weld looks like the outside. Now, had we not back purged it, and we could do that for you real quick, we could just weld on a piece of tube, and when you see the back side of it, you'll go, oh, that's why people back purge. Okay, so real quick, I just welded these 2 pieces of scrap tubing together. And we don't care about the joint or anything, but if you look, it's not a bad weld. It has decent color and whatnot. But now, let's look at the backside of that weld. See how it's all gray and purple and lumpy and looks like a bunch of crystals or breadcrumbs, or it looks like a crumb cake in there. That'll fall off. And if this was a turbo header, yeah, it looks like an ashtray. That would go through your turbo if this was a turbo header. And more importantly, it's definitely not as strong as it could be. And if you saw this, say this was a header, and you looked on the outside, you go, that looks okay, you know? It's what's behind it that matters. Look in there. That sucks. That's why we back purge.
Ooh. Oh, dude.
Is this gonna work?
No.
No way.
That easy?
Yeah, that easy.
No way.
That's because fender well headers for the win. If they went straight down, I don't know. They might not come out.
Those things look good.